Hi, today we're going to get started in chapter 4. The first thing in section 4.1, it introduces the mod operator. So there's two different ways to kind of express this. Well, there's probably dozens of different ways to express it, but the standard one in the math world is to write something like this: x mod n. And that just means, what would the remainder be that you get if you divided x by n? In other words, it's the r, where r comes from the quotient remainder theorem, or the division algorithm, as they call it in this book, where r I just wanted to say it in words first, but what this means is that x there could be written as a quotient times n plus a remainder. So a consequence is that this value x mod n, since it's the remainder, the biggest it can be is actually n minus 1. It's going to be smaller than n. It'll be 0 or larger, but so remember the inequality that goes with this statement, that r lies between 0 and n, inclusive at the low end, but not inclusive at the high end. So possible values for x mod n are 0 through n minus 1. Okay. If you do this in Sage or many computer systems, they write this with a percent sign. So x percent n would be how you get to the value of r. There's another way to do it in Sage, which is, I always mix up the order, so give me a second to check. It's in here, I know. You say mod, so the modulus comes second. But these are subtly different. They allude to this in the textbook a little bit. Let me just point it out to you. This one, when you say x percent n, you get a regular integer, just a regular integer. When you do this, you get an element of a certain ring, the ring of integers modulo n. If you check out what the type of something that's returned by that mod operation is, it's not just an integer. And that's appropriate because these moduli work in a really nice way with one another. They've got more structure than just being integers. I just used the word. So everybody shortens this to mod, but in fact the word is modulo that goes in there. I should have probably pointed that out to begin with. Mod is shorthand for modulo, which I think is Greek, but anyway, whatever it is, the full word is modulo. And modulus is this number, the n. And if you're doing multiple of these things, say you're taking some numbers mod 5 and the same numbers maybe mod 7, then you will have the plural form of modulus, which is moduli, which is what I just used a second ago without saying what it was first. Oops. All right. Let's do a quick example or two. Right? I think many of us have seen this before. Most people's Math 250 course would have had some treatment of the mod operator, but let's do an example. Pen cap. How about if I did 42? I started to say 42 and then wrote the mod. 42 mod 13. I'm doing this example because I want you to learn some of the mental shortcuts you can take to figure this out. What you want to do is look for a multiple of 13 that comes somewhere before this. Do you notice that 39 is 3 times 13? So basically spotting the q times n piece, that's the quotient, that's the n, allows you to figure out what the remainder is real quick just by counting up. From 39 you go 40, 41, 42. That thing is 3. 42 mod 13 must be equal to 3. Let me do another quick example. How about if I did 145 mod 12? I picked that one because I think everybody knows that 144 is a gross, or a dozen dozens. So 12 times 12 is 144. That means this thing is just one bigger than a multiple of 12, so it's 1. All right, so I guess that's enough for examples. There's a new concept we get, which is a relation between numbers that says, as far as mod is concerned, they're the same. They're not really the same, but in terms of mod, they're the same. So it's called congruence. Basically, you write it something like this: x is congruent, triple bar equal sign, to y mod n. And what it really means is these two numbers have the same remainder. We're going to come back to this point, but this is how you should actually think of it, I believe. It means that x mod n and y mod n are equal. But that is not how we define it. So we're going to come back to that and prove that that is the case, and that really is the fundamental reason that we would write the congruent symbol between things. But the definition is slightly different. So let's say what the definition is. Let me make sure I'm not skipping something. I did skip something. I was going to show you an alternate notation for that. Let me just stick it off in the corner a little bit, just because sometimes there are multiple n's around and you get a lot of these parenthetical mod n bits at the end, and it becomes easier to put a little subscript on your congruent sign. So you could also write x is congruent mod n to y. That's less common, I think. I usually write it all out, but you occasionally will see that. All right, so what is this formal definition I was alluding to? It's this. X is congruent to y mod n if and only if the difference between these two things is divisible by n. So greater is n divides into x minus y. So let's do an example of that, and we'll verify that the definition holds for this thing, or this pair of things. Suppose x was 143 and y is 71, and we're working with n is 12. So this isn't what we're supposed to do, but I wanted you to check what are the remainders on these two guys when you divide them by 12. You may have noticed that I snuck something in there. I made this guy one smaller than 144, and this one smaller than 72. So these guys are at the position right before a multiple of 12. what's the, right before a multiple of 12, it's sort of like -1 mod 12, but we don't have -1s because these are supposed to be remainders. Remainders are in the range from 0 to 11. And that's what these guys are. That's 11 times 12 plus 11. This is 5 times 12 plus 11. If you're 5 feet 11 tall, that makes you 71 inches tall. Okay, so these are both 11 mod 12. We should be able to write the congruence between them. To check that that is correct, what we need to do is, well, let me put it this way. We claim that x is congruent to y mod 12. And the way we deduce that is check whether 12 divides into x minus y. Well, x minus y is equal to, 72. And 12 does indeed divide into 72. 72 inches is 6 feet. So yeah, that's it. You've just proved the claim. I don't know what this to do other than put a period there. Maybe put it like a check mark saying, yeah, we did it. All right, so let's go through proving that this idea of subtracting the two numbers and then checking that it's divisible by the modulus is really the same thing as what I claimed before, that the two numbers give you the same remainder, well, or when divided by n. Well, that is in the book, but there's only a sketch of the argument. So what is that sketch about? First of all, he phrases it as a lemma. Oh, I'm in the wrong section. Sorry, excuse me one sec. Here we go. Lemma 4.1.2. All right, so here's what it says. It says, let me say it in words. It says, saying A is congruent to B mod n is exactly the same thing as saying A and B leave the same remainder when divided by n. I wonder if taking a video of my screen here is of any use. Weird. Does that work at all if I show you that lemma by photographing the screen of my laptop? It's 4.1.2, and the proof is one of those expandable things. I'm trying to use my touch screen, and this isn't a touch screen. There we go. Let me show it to you. He says this, we can... Well, I was having a slightly frustrating time trying to get to the camera to focus on my laptop and holding multiple things at once, and then the power went out on... Bad language was used, so I thought I'd spare you that, and it was edited away. So I was trying to show you this theorem or lemma, really, at its proof in the book. The lemma is 4.1.2. And it's just, he said it in an informal way, saying that A is congruent to B mod n, that in other words, A minus B is divisible by n, is exactly the same thing as saying A and B leave the same remainder when divided by n. I find it a little, well, maybe this is a good thing. He doesn't go through the proof in detail. What he does is he provides a sketch and then asks you to kind of fill in the hard piece. So I thought it would be good for me to fill in the hard piece. So it says, in the phrasing there, it says, it's exactly the same thing, which is one of many euphemisms people have for if and only if. A is congruent to B mod n, if and only if A mod n and B mod n are equal. That's what we're really trying to prove. So this is really, well, the first bullet here is just setup. If you're going to claim that things about A and B and what their remainders are, then you ought to use the quotient remainder theorem. He didn't state that, but he asks you that. Why is this possible? Why can we write A as n times q plus r and B as n times q prime plus r prime? It's because of the division algorithm, or the QR theorem. And then once you've got that set up, what do? Well, you first show that if r and r prime are equal, then you'll have the congruence symbol, or the definition of the congruence, and then you do vice versa. So it's an if, and then it's an only if. All right, so if r and r prime are equal to each other, wow, that seems like they jumped a little bit, doesn't it? First, if r equals r prime, let me highlight that, then there is a case such that a minus b equals nk. I'm not seeing that right away, but if you look at these two forms, nq plus r and nq prime plus r prime, well, those things have actually the same number on the end there. So if we subtract, form a minus b, you'll get nq minus nq prime. So what's this k they refer to here? It's q minus q prime. Okay, so that direction actually is pretty straightforward. It's the other direction that I think is tougher, a little bit tougher anyway. He even says this. This is a little harder. So let's go back to the whiteboard and I'll show you that. All right, so we're back to the board here. The thing we're trying to prove then is lemma 4.1.2. It's that, well, ultimately it's this, that if two things are congruent mod n, that means they have exactly the same value for the remainders, or another way to put it is x mod n and y mod n are equal to each other. Because that's a way to refer to the remainder when you divide x by n. So let's see, I think we did the back direction already. We sort of talked about it. That direction is easy. Because if these guys have the same remainder, then when you subtract, the x minus the y, you can, well, I guess maybe I should say it's easy, but let's do it. Yeah, let's straighten that out. So I'm actually illustrating bad form right now, so I'm going to fix that too. We're going to first start by writing that this is the proof, and the first part of this proof is going to be showing the only if part of our segment. So we're going to assume that x mod n and y mod n are equal. That should be probably in parentheses. So I think, yeah, you know what? We should probably do just like they did in the book, which is do a little setup first. Let x be written in the quotient remainder form, so q times n plus r, and y would be q prime times n plus r prime. That's by the QR theorem. I'm just abbreviating it because I don't have space to write it more, but the division algorithm is another way to say it. Okay, so then we're going so that's sort of set up first. Now we're working on the only if phase of this, proving this if and only if. So we assume the right hand side. We assume that these two things are equal. So what does that mean? Well, because of the form we wrote them, that means R and R prime are equal. Okay. Well, and then what we want to do is show that X is congruent to Y. But remember what the definition of that is that the difference of them is divisible by n. So what we're going to do is look at the difference. Well, X minus Y is equal to, because of the form, oh, so where is it? Because of the form we said, this is equal to Q n plus R minus Q prime n. I'm going to write plus R here because on the situation we're in, R and R prime are the same. So I could replace the R prime with just an R. And that means that when we have an R here and a minus R there, they go away. So what we have there is just Qn minus Q prime n. And finally, well, I want to show that that number is divisible by n, and it's actually pretty clear, isn't it? You can factor an n out of both sides of that, and you get an expression that looks like n times an integer. I guess that's the end of the sentence, so put a period there. The conclusion then, though, is that is obviously the right thing that will tell you that the number x minus y is divisible by n. So therefore, n divides x minus y. And what does that lead you to? Well, that's the definition of x is congruent to y. All right, so that was the only if. Let's do the if phase now. Let's see, what does that mean? Well, here we're going to be assuming x is congruent to y, mod n. Now, I'm not going to break the line so that I conserve a little bit of space. Assume x is congruent to y, mod n. By the definition, that gives you, well, something that looks like this. N has to be a divisor of x minus y. Now, in this branch of the proof, I haven't gotten to this point yet, that r is equal to r prime. In fact, that's what I want to get to. Okay, so we can't use that because, well, we're in a different setting right now. But we can use that x and y can be written in that quotient remainder form like we had in the initial setup. So we'll do that here. X. Let's replace x with what it's equal to. N is going to divide into Qn plus R, that's what x is, minus y is Q prime n plus R prime. Well, that is somewhat simplifiable. You've got Q minus Q prime times n plus R minus R prime. Now think about what that says. You've got a number n that goes into something that's clearly a multiple of n plus some other guy. And so I think it probably just makes intuitive sense that that means this other thing has to be divisible by n. Let's try to make that more rigorous though. Well, if n divides that number, that means that that number is some constant times n. So by the definition of divisibility, I'm just going to abbreviate that. What do we get is that q minus q prime times n plus r minus r prime is equal to some constant times n. And that constant k has to be an integer. Well, if we just rearrange this so that we basically solve it for the parenthetical bit there, r minus r prime, we get well, it'll be k times n minus q prime times n, and that's all a multiple of n. I guess I can do it one last time. N times k minus q plus q prime. The only thing we need to know though is that this is a multiple of n and this bit here is an integer. Well, which multiple of n is it? You see, if this difference is 0, then we're good. We've got a well, if the difference is 0, that means the r prime and the r are equal, which is what we're trying to get to. But if the difference is not 0, you can think, what's the smallest it's going to be? Let me go ahead and say this. If r minus r prime equals 0, then r equals r prime. So our conclusion holds. That is that x mod n is equal to y mod n. I'm really trying to squeeze it in there so we get to, sorry my board is short. Otherwise, and I want to say without loss of generality otherwise, if r and r prime were in the order so that this difference came out negative, then I could just change which one I call x and which one I call y and arrange for that also. So otherwise, without loss of generality, we have that r minus r prime is at least 1 times n. So it could be 0, in which case we're done. It could be 1 times n, it could be 2 times n, it could be 3 times n, but this deals with all those cases. It's a positive multiple of n. All right, that's good stuff. Why does that help us? Because I'm trying to show that this isn't the case. All right, that in fact r minus r prime is 0, and that means r is equal to r prime, so the conclusion is valid. Well, why wouldn't this, can we find something that this is contradictory towards? Yeah, we can, because I know that r and r prime there satisfy certain conditions. What we know is that 0 is less than or equal to r, which is less than n. And similarly for r prime, And what I want to show you is that the difference r minus r prime is actually less than n, in contradiction to that fact. So this thing we just deduced is, without loss of generality, it's greater or equal to n, and I'm going to show you that it's less than n. And what we're going to do that by highlighting parts of these inequalities. I know that r is less than n, right? And I know that r prime is greater or equal to 0. So what do those two things tell us? If r is less than n, right, and then we subtract something that's 0 or larger, that value gets smaller. Meaning the two of these things together imply that r is, the difference, r minus r prime, is less than n. And that's a contradiction. The two arrowheads butting is sort of chalkboard or whiteboard shorthand for a whole sentence that says, this is a contradiction, therefore the original assumption was false. And well, that means that r minus r, sorry, where to go? The otherwise here. So on the one hand, we had the difference was 0. The otherwise leads to a contradiction, so there is no otherwise. We're just in the state where r minus r prime is 0. Okay, so that was a little bit of a tough argument, but it's not really that bad. There's some uses of this mod stuff that come up next in the book that I think are kind of fun. So let's look at that. One of the ways in which mod can be used is just as a really good shorthand for stuff. So there was a statement that you talked about back in chapter 2, that a number squared divided by 4. So that is, if you took x squared and you figured out it was, let's see, some quotient times a number n. Well, actually, let's do it for 4. Q times 4 plus a remainder. If you had a setup like that, then the remainder could only be two things. It could be 0 or 1. And this, of course, is for an integer x. I should be more careful. I wanted this to be the quotient remainder theorem statement, so I have to put on the proviso that goes with that makes this a unique expression, which is that r, all right, not quite there, 0 is less than or equal to r is less than 4. We're thinking about dividing by 4 and getting quotient remainder form for that. So yeah, but we only have two possibilities for remainders. You can't have a square that's 2, and you can't have a square that's 3, mod 4. Oh, I'm using the language of mod already. See, this whole statement turns into something a little bit easier, I would say, when you talk about mods. It says that, well, let's actually properly state it with quantifiers and everything. For all x in the integers, x squared mod 4 is in the set with only 0 and 1 in it. A way to refer to this is the phrase quadratic residue, which, I don't know. It's fancy terminology anyway. It sounds kind of good to use that. Quadratic residue. Quadratic because we're talking about squares. Residues are an old-fashioned way to talk about the different values you get when you take things modulo some number. In this case, we're talking about residues mod 4. So all possible residues are 0, 1, 2, and 3. The quadratic residues in this case are just those, 0 and 1. Let's give another example of a set of quadratic residues. Consider mod 7. might even help us if we make a little table of this. Let's see, am I going to have space for it? Probably just barely. I want to think about x, and then what x squared is, and then finally, what is x squared mod 7? Of course, when x is 0, x squared is 0, and mod 7, you don't have to do anything for a number that's already the right size to be a remainder. 1 squared is 1, yep, still don't have to do anything. 2, 4, still not big enough to need any reduction to figure out what it is, mod 7. But 3 does have a problem. You see, 3 squared is 9, that's bigger than 7. Bigger than or equal to 7, anyway. What's 9 mod 7? Oh yeah, okay, it's 2. What is kind of interesting is that's it. Those are the numbers that you get as quadratic residues, which you can think about in multiple ways. First, I could go ahead and continue the table, but you might think about what comes before 0. -1, I guess, but -1 is not really the right size to be a residue. But -1, here's the way I usually think about it. You've got a clock with the hours 0 through 7 on it. Those numbers are 1, 2, 3, 4, 5, 6. I've got a clock like that, and these are the values of the residues. But if I think about -1, it's just 1 hour before midnight on this 7-hour clock, so it's 6. Well, what do I get if I square 6? I know I could do this the hard way. I get 36, and that's just a little bigger than 35, which is a multiple of 7. But I'd rather think of it this way. 6, it's the same as -1. And the square of 1 and the square of -1 are the same. That's what squaring does. It takes, kills off the minus signs. Well, let's go ahead and do this the old hard way instead. 4 squared to be 16. What's that? How much bigger than a multiple of 7 is that? Oh, it's 2 beyond 14, isn't it? Get 2 there. 5. I am not going to be able to fit 6 on this little table, but anyway. 25. Is it square? 21 is the nearest multiple of 7, so this is 4 beyond that. So you see what happened? You got 0, 1, 4, 2, and then you got 2, 4, and I tried to argue that the next row, which would have 6, 36, and 1 in it, is that. So the squares work this way in mod 7. They go 0, 1, 4, 2, 2, 4, 1, 0, and repeat. It just keeps going through the same cycle of 7 digits. So what are the quadratic residues? Excuse me, I can't seem to get it to right there. The quadratic residues mod 7 are 0, 1, 2, and 4. So no square will ever be 3 mod 7. No square will ever be 5 or 6 mod 7. Just those are the only possibilities. Okay, that's the end of section 4.1.